Okay, I see we have 98 viewers now, so welcome everybody. I'm going to introduce this year's 2026 winter school from the Center for Quantum Networks. We'll be having 10 courses over the week. Each course is about 3.5 to 4 hours long. And myself and Francesca Sansavini will be presenting today's first course, which is a gentle introduction to the concepts and the physics behind quantum networks. And just to say a couple of words, the Center for Quantum Networks is a National Science Foundation funded project, which encompasses many universities in the United States. We're working to facilitate quantum networks. Okay, so 1 second here. Let me get started. Welcome everybody to the first short course of the 2026 Center for Quantum Networks Winter School. I'm Professor Michael Raymer at the University of Oregon, and the co-instructor today, who's helped to prepare and present this course, is Francesca Sansavini, also at the University of Oregon. We'll be talking about the physics behind the quantum internet from the point of view of an introduction, and let's get going. So the first poll question, if the first poll question could be shown, I'd like everybody to practice your poll answering. Do you see the poll question there, Francesca?
I see it now, yeah.
There it is. Okay, everybody, please click on one of your favorite answers here, explaining this. Okay, good. So we have quite a broad range of people, and welcome everybody. We're trying to make this course accessible to all of you, those who are new to quantum theory, those who learned the Schrodinger equation in school, but not much about quantum information, and also those who already have a PhD or master's degree, but are interested in possible ways of communicating to the public how to teach quantum information to non-experts. So that's what we're moving along towards here. So that we have these in 4 parts, and Francesca and I will share the presentation duties here. We'll talk about the general basics of quantum information science. We'll talk about entanglement and how to encode information in quantum states. We'll talk about photon entanglement and applications, and then we'll finally wrap it up with how the quantum internet is supposed to work. Okay, so part 1, the physics behind the internet, the quantum information science. So a motivation here is the following, that quantum science and technology is based on 3 science and technology pillars or areas. First one being quantum computing, which we won't talk about much today because we're focusing on quantum networks, but I'm sure you've all read things in the media or are actually working yourself to build quantum computers. Then there's quantum sensing. And the idea here is that using quantum systems, you can be more sensitive to environmental parameters or disturbances than you would be without having quantum techniques. And finally, as we'll focus on today, quantum communication provides secure data encryption and other applications that we'll talk about in more detail. And finally, the quantum network is meant to link all of these technologies together, just like the current day internet links all computers and all communication systems together. So we'll see how that is done in the quantum world and why it's so different to implement in the quantum world than it is in the current existing classical internet world. Okay, so what could a quantum network do? We just talked about a couple of those things, but we won't have time to discuss these in great detail. But you can see that there are many different applications. Francesca will talk about quantum key distribution, which is secure encryption. We won't talk much about quantum computing or databases. We won't talk much in detail about synchronization, although we will discuss synchronization a little bit because it will be necessary to implement the network technologies. And we'll talk a little bit about sensing, but not very much. Those are special topics. But the point is that if you can implement all these, which by the way have not been implemented yet, in the next 10 years, we might be able to implement these technologies, which could actually revolutionize the information world that we live in. And finally, we can also implement new physics tests, like testing quantum gravity and studying black holes and other exotic topics like dark matter. And this physics test is really what is driving many physicists like myself to study this field, as opposed to just building, databases or encrypted systems. We're very interested in how the deep understanding of quantum information science can inform all of science, at least all of quantum physics. Okay, common misconceptions. The quantum internet will not be able to instantaneously cause an effect across the large distance, will not be able to enable faster than light communication, unlike in most science fiction movies in which they break these rules. But these rules are steadfast rules that are founded on relativity theory and quantum physics. And on a practical matter, number 3, you cannot increase the data rate compared to classical networks. So if you can't do those things, what can you do? Well, I just showed you the things on the previous slide, what you can do. And those are equally important as these science fiction topics, which we cannot do. Okay, so on into the technical business here. What is classical information? Well, in the context of computer science, information is simply the set of symbols that are sent. It doesn't have anything to do with the meaning of the symbols. It just has to do with essentially the quantity or how many symbols you've sent. And in computer science, we only use 2 symbols, the 0 and the 1. That's called binary. And these are binary bits. And here's a list of typical, the first 10 or 11 binary numbers. Okay, so this whole binary information theory business was worked out first in 1948 by Claude Shannon, a very famous person. If you don't know this person by reputation, you should look him up on some YouTube videos and learn about Claude Shannon. He was a fantastic hero of the field. But that was classical information. And what is that? Well, he talked about bits. And a bit is something that can be 1 or 0, it can be on or off, it can be blue or red. It just has 2 possibilities. We call the condition of this switch, for example, light switch, its state. And this word state will be used many times in the lecture here. Okay, so the position of a light switch is an example of a classical state. That's not the same as a quantum state, which we'll get to in a minute. Okay, so poll question 2. So if you could put the question up, please. So you can move the box, you can grab that box and slide it to the side to get it out of your way, and then read this question and answer the question. And Brigia, you can tell me when we have 80% of people. We'll do that. We'll either get to 80% or we'll do 5 seconds to the end.
Yeah, we
Okay.
have generally 70% answered.
Okay, very good. Thank you. Okay, so most people said it's item the second item number 4, and the answer is 4. So that's fantastic. And here are the 4 possibilities. First of all, notice that if we have two switches, two physical bits inside of a memory cell, this green box here, and then we talk about the combined state of these 2 switches. And I use an ampersand, which means and. So I have the first switch and the second switch. And we have to specify the state inside the box. There's 4 possibilities. Here's one possibility, 0, 0. Here's another one, 0, 1. Another one, 1, 0. See, I'm switching those switches. If they're both up, I have 1, 1. So that's our 4 possibilities. And here they are shown all together on one page. Okay, so the point is that if you have 2 switches in a memory cell, you can store one of these 4 combinations. But of course, you can't store more than 1 combination. You have to pick one or the other and only store one of them. And that's how computer memory cells work typically. Okay, poll question 3, please put it up. Okay, most people said 8, which is exactly correct, because 2 times 2 times 2 is 2 to the 3, which is 8. And there are 8 unique combined classical states of this memory cell containing 3 switches. Perfect. Okay, now in quantum information, we're going to go to that right away now. Let's consider just a single switch, which is called a quantum switch, or a quantum bit, which is abbreviated qubit. This is just a picture of one switch. Forget about these other two pictures. Just look at this one switch. This switch can be up or down, 0 or 1. But now, in quantum physics, we can have what's called a superposition state. And when you symbolize that by a plus sign, it doesn't really mean plus. It just means in superposition with, as I said over here. So we have a switch, and the single switch is in a superposition of being both up and down together. And we represent this by this picture of a switch with a question mark on it, because the state of the switch is not determined. It can be either up or down. Now we call this states 0 and 1, and we use this little bracket notation. And then we have these coefficients called x and y. Those are just numbers. They can be any number between 0 and 1. And the rule, due to Max Born, who was the co-inventor of quantum physics, is the following. At the bottom, he first pointed out, it's meaningless to ask, is the qubit 0 or 1 before it is measured or observed? So if this switch is in a dark vacuum chamber and nobody's looking at it, and it's in a superposition, it's really not true that it's either 0 or 1. It's neither. However, when you observe it, you turn the lights on and look at it, then you have a probability to observe it as a 0 or 1. The probability to observe it as 0 is a number x quantity squared, and the other probability is y squared. Now, these have to add up to 1 because the probability that when you observe it, it's going to be either 0 or 1, that has to be a certainty, which is 1. So the probability to observe either 0 or 1 adds up to 1. So that means x squared plus y squared should equal 1. No matter what the value of x is, y should have the corresponding value. So that x squared plus y squared is 1. And this actually goes back to Pythagoras, or even earlier in Babylonia. That's just the Pythagorean theorem for a triangle, where the hypotenuse length is 1 and the two sides have values x and y. And those x and y are these coefficients that are multiplied in front of these quantum state brackets. Okay, that's pretty much all the mathematics you have to know for this lecture. Let's do an example. So let's show the poll question, please. Okay, most people said, yep, that is correct. Most people said 9 over 25 because that's just equal to 3 over 5 squared. Okay, so whatever the number sits here, in this case, 3 over 5, 3/5, that's x. And you square that number to get the probability that you'll see the 0. The square of the other number, the square of 4 over 5, is the probability that you'll get the value 1 if you observe the qubit. Okay, so even though there's probabilities, and you can think of that as like flipping a coin, an unfair coin, it's not the same, because with a coin, if you flip it and it sits there on the table and you don't look at it, before you look at it, it has a certain value. But in a quantum state, that's not the case. Before you look at it, it actually doesn't have a value. But then when you look at it, a value emerges from quantum physics. That's not well understood in the real world, how that happens. But millions of experiments have shown us that that's exactly the right way to look at it. Okay,
Mike,
now, yes.
I'm gonna interrupt you a second. There is a very good question by Janavi that asks, what is the difference between classical uncertainty and quantum uncertainty while speaking about probability?
Yes, it's more or less what I said. Let me try to repeat it. In classical uncertainty, the situation is that there's a state in the world, like the switch is on or off, but you don't know it. And so you're classically uncertain. But in quantum physics, before the qubit is observed, you're also uncertain about what you're going to observe when you do observe it. But the fact is that the qubit doesn't have a value 0 or 1 before you observe it. So in this case, it's the uncertainty about what value is going to emerge when you actually observe it. And that's a very deep point, hard to explain in words, but that's the difference. So let's go on. Maybe it'll become more clear. Okay, so an example of a physical qubit is a single atom. And if you have an atom floating in a vacuum chamber, like I've shown here, a photograph, this is an actual photograph of about 50 atoms floating in this little vacuum chamber. And if you just look at one of the atoms, it has a bunch of electrons, but let's just consider a single electron in that atom, the one that we can access by shining laser light onto it, as I'll show much later. Now, this electron you can think of as a little top. It spins on a certain axis. In this case, we call it the vertical axis. It's spinning. This is clockwise. If you look down on it, it's spinning clockwise around and around. And that corresponds to a switch that in the up position, so I'll call it a 1, okay? Now, it can also spin to the left or counterclockwise, but in fact, it can also be put by using laser control. The spinning electron can be put into a quantum superposition state of spinning counterclockwise and spinning clockwise simultaneously. And it looks like this in the context of switches. Again, the plus sign simply means superposition state. Okay, that's a very strange thing, and you cannot have that classically. A classical switch cannot be in a superposition of on and off, but a quantum switch can be. And that's the essential difference that leads to the capability for quantum computation and also quantum communication. Okay, now in a quantum internet, here's a picture, and we typically use photons. Well, we have to use photons to transmit quantum information from one location, 1,000 kilometers to another location across optical fibers or possibly through satellite links. Now, these are photons. These are particles of light. And so let's talk about that in great detail, okay? So what is a photon, okay? Well, as I said, it's a particle of light. So let's think about how we would do an experiment. And this experiment was actually done in the 1980s, actually in Paris, France, I believe. Now, the experiment is you have a single atom floating in a vacuum chamber, and you shine a very dim light beam at it. It could be a light laser, or it could be a light bulb. Now, sometimes this atom will absorb some light, and then it will emit a photon in some direction, any old direction. But there's a barrier here with a small hole in it. And sometimes light goes through this hole. And then after this small hole, there's a beam splitter, which is simply a piece of glass that one surface has been partially coated with metal. And so the light can either pass through it, in which case it'll hit this detector, or the light can reflect from the metal surface and bounce off and hit this other detector. Okay, now what's going to happen if this light beam is very dim and there's only one atom? We're getting down to the quantum level. Okay, so put the poll question up, please, here, and look at this picture. Okay, let's see the results. Okay, most people said A, and some people said B, or I don't know. Okay, that's good. This one is not so obvious. Okay. Now let's think about this. It's in the limit that the light beam is very dim and there's only one atom. So that if these detectors are very fast or quick, and that's what these little slots are, these time slots, because here we're looking at a time sequence, and assume the time slots are very short. So during a very short time slot, either just one of the detectors could register an event, which means light struck the detector. We call it a click, or sometimes maybe both could do so. Now, as we make the light beam dimmer and dimmer, what the experimenters found is actually that the correct answer is 1. It's the top possibility. If you have very bright lit light, you can see the possibility of number 2, which means both detectors could click at the same time. But as you make the light dimmer and dimmer, you get more and more times when there's no click, and sometimes when only one detector clicks, but never if both click. And what that is telling us is, in fact, that the light is kind of like partitioned into what you think of as particles. So if just one particle is traveling here and it hits a splitter, that particle can either go to A or B, but it cannot go to both. And the only way you could have them both click is if this atom emitted 2 particles of light. But if the light beam is very dim, that means the particles of light are coming very rarely, and so they never overlap. And so the answer that was observed in the experiment is number 1. And I'm going to move right along and show that. This is the correct answer. So this shows that light behaves like little particles, and that the more dim the light is, the fewer particles per second there will be traveling in the light beam. Okay, that's just the way nature works. That's not obvious, but that's the way the world is built, and that's the basis of quantum physics. Okay, so it's random, and this goes to one of the question was just asked. What does uncertainty mean? Well, there's discreteness, which means only one detector clicks at a time, but there's also randomness because you cannot predict which one it is. Now, I said earlier, just a second ago, that the particle either goes through or it bounces off. Well, that's actually not quite true. I told a not true statement. If you remove these two detectors, the detector A and B, and so the light path is unblocked and goes on for millions of miles to the right and millions of miles to the bottom, actually, it's not true that the particle takes one path or the other. It's actually in a superposition state. So that's the quantum uncertainty. It's only when you put the detectors there that the photon or light particle has to decide which detector it's going to make click. So that's a very not classical type of uncertainty. Okay, so here we're showing a click, and this is what we call indivisible light particles, which are called photons. Okay, now how do we use these photons to encode information? That's what we have to do. Well, now I'm going to change the story on you and talk about a wave property. After we just talked about particle properties, we now need to talk about wave properties. Well, light is also can be correctly viewed as a wave. Polarization of light corresponds to the way in which, or the direction in which, the light's electric field oscillates as it travels. But what's an electric field? A field is something that establishes a force between objects that are not in direct contact. For example, the moon is attracted to the Earth because there's a gravitational field that establishes a force between them. Okay, that's a field. Well, there's also electric field. And here's an example. This is a metal wire that's in the vertical direction. Here we have a light wave that's coming in. I'm showing its oscillation in the up, down, or the vertical position. Now, if I have in this metal wire a proton, which is a positive charge, and it's able to move up and down inside this wire, then as I move the light field through it, the proton is pushed in the same direction that the electric field arrows, these little tiny arrows here, are pushing it, okay? But now if I have an electron over here, the electron is negatively charged, and so it actually gets pushed in the opposite direction. So watch this animation. As the field goes by, when the field is positive, the electron gets pushed negative. And when the field is negative, the electron gets pushed positive. This is how radio works. Okay, you can think of this metal wire as an antenna, which is what's in your cell phone. And the electrons in your cell phone antenna are oscillating as radio waves pass by. But the same thing is also true for light waves. Light waves are the same as radio waves, except it has a much higher frequency. Okay, very good. Now, if the light wave is horizontally polarized, so it oscillates in the horizontal plane back and forth, and the wire is in the vertical position, nothing happens because the electron is not able to be pushed outside the wire, so it just sits where it is. No motion. Okay, but now if I move the wire so it's rotated horizontally to the same orientation as the light wave polarization, now again it can react to it. So this is how light polarization works and how electrons respond to light polarization. Okay, now we're not going to use wires. We're going to use electrons in atoms. Remember I showed earlier an atom and it has an electron spinning. So that was a different way that the light can interact with the electron. It can make it spin. Instead of moving, it can make it spin on its axis. And that also depends on polarization, but that's complicated. We don't need to talk about how that actually works. All right, so now we have these little pictures here encoding in a cartoon manner these four polarizations. So if you look from your eyeball on the end of the light wave that's traveling away from you. Like say you put a laser pointer right by your eye and you shoot it away from your eye, obviously not into your eye, and you're looking at the light beam as it goes away from you. You could, if you could see polarization, you could see it oscillating vertically up and down, or you could see it horizontally oscillating, or you could see it at a diagonal. We call this D diagonal, or A is anti-diagonal. And in fact, it could be oscillating in any direction. And in fact, sunlight has light that oscillates in all directions simultaneously. It's a mixture of different oscillations. But we'll normally treat these 4 different cases as simple examples that we can use to encode information, as you'll see. Okay, now, next piece of technology that we need is a light crystal called a calcite crystal. And you can buy these crystals in a rock store. And they're just transparent crystals. If you can see my face, I'm actually holding one up right now in front of my face in the little tiny picture there, a little crystal, transparent crystal made of calcite. If light goes through a calcite crystal, it's actually split into 2 different parts or paths. One is the horizontal path, and the other is the vertical path. So in other words, light that's horizontally polarized will go straight through the crystal. Light that's vertically polarized will be deflected into a different detector. So that's how we can separate and therefore measure the polarization of light. Okay. If we rotate the crystal by 45 degrees, we call this a DA-oriented calcite crystal. The first one is called a HV-oriented calcite crystal. The measurement scheme is a word that refers to how the crystal is oriented. And you're the experimenter. You can rotate this crystal and arrange it to any angle that you wish. So if you have sunlight coming in here, or if you have a state of polarization that's not known, you can split it up into these 2 different components, the anti-diagonal and the diagonal, or you can split it into these two components, vertical and horizontal. Okay. Now here's a poll question. Please put the question up. Brigia. Okay, there's a mixture of answers here. So let me discuss this for a second. So here we have a dim light beam, as we had before. A single photon is passed through this small hole and enters into this calcite crystal. Now, if it goes to this block, it goes away and never seen again. If it goes to the vertical path, then it goes to the upper path and goes to the second crystal, which has the same orientation as the first crystal. So in this second crystal, we already know what the rule is for the second crystal. Now, we know that this light, even though we didn't look at it, we know it's vertically polarized because nothing hit the block. Say we put a detector at the block and nothing hit it. So we know there's a photon in the V polarized orientation. Now we put it through a second crystal. So now the question is, it could either go vertical again or it could go horizontal. So show the poll question again, Brigia. Same question. We'll do this one again. Okay, yeah, there's more people now that voted for the upper, and that's actually the correct answer. The reason is because when you make a measurement on a single photon, if you measure it V the first time, because you know it was in the V path, then the second crystal just acts like the second measurement of the same quantity. So it's already V, so it has to be V again. It doesn't get changed by this kind of a setup. However, now consider this different case. I now take the second crystal and I rotate it by 45 degrees. So now what it does is it separates this photon into 2 possibilities, anti-diagonal or diagonal. So poll question, please. Okay, now it's, oh, excellent. Look at that. See, 72% respondents said either, and that's correct. Because now the photon is known to be vertically polarized, but when it goes through the second crystal, it doesn't know which way to go. So the answer emerges through some mysterious process of quantum physics. The quantum uncertainty is resolved by making the measurement. So again, the photon, before it hit the second crystal, was V polarized. That doesn't mean that it was either A or D. It's not A or D, it's V. And so by making the measurement, you have forced the photon to make a decision. I'm going to be A or I'm going to be D. And it could be a 50-50 probability. Okay, that's called quantum superposition. So I think you're maybe getting the idea for those who are new to this subject. Okay, now I'm going to take this cartoon and talk about the D and the A and represent it by a little graph here. So looking edge on or end on to the photon, if the electric field is oscillating in a positive diagonal direction, we call that depolarization. If it's anti-diagonal at minus 45, we call that apolarization. Notice if I think about a graph, the H component is equal to the V component. They're both positive. In fact, they're 1 over root 2 because x squared plus y squared has to equal 1 according to the probability rule. So each value has to be 1 over the square root of 2. And the plus means in superposition with. Now the apolarization is the same, except the H component on the horizontal axis here has a minus 1 over square root of 2 projection onto the h-axis. That's the only difference. So it's a minus sign. The probability is still 50-50 or 1/2 because minus 1 over the square root of 2 squared is still 1/2. The difference, though, is in the direction that the oscillation is taking place. And in general, the oscillation can take place at any different angle. And we indicate those angles by these projections x onto the h-axis and this projection y onto the v-axis. So this is where we get this representation of the mathematics. X is any number, that's the projection onto this axis, and y is the corresponding number for the other axis. And we use h and v to indicate the quantum states of h and v. Okay, so these equations are going to be used as we go along in the lectures. So D is h plus v, and A polarization is minus H plus V with some other root 2 factors. Okay, that's the second large piece of mathematics we're going to use. And here we can show it in a graphical form. Actually, I have a little piece of graph paper here. And we indicate the arrow, like on the previous slide, we had this little oscillating picture. But now we're just going to indicate the tip of the arrow by the tip of this oscillation by an arrow. Okay, this is the next level of mathematical abstraction. So we're going to talk about an arrow just indicating the direction in which the oscillation takes place. So if the arrow is pointing to the H, we call that arrow the psi symbol. That's the quantum state, psi. And if it's pointing to the H, that means that the oscillation is H. So it looks like this. If we point the arrow to the V symbol, that means we're talking about a state in which the photon is oscillating in the V direction. If we point the arrow halfway between in the superposition, then that's 0.71 V plus 0.71 H. 1 over square root of 2 is 0.71. And if we point the arrow in this other direction, that means the projection onto the H-axis is negative. So there's a minus here. So it's 0.71 minus H. So this is how we mathematically represent those 4 quantum states of a single photon. Okay, moving right along. The quantum state is not a property of the photon. It's actually just a description of the photon, if that makes any sense to you. That's a slight difference. Okay, we can point that arrow in any direction, and then we can analyze the probability that this photon will strike one of these 2 detectors if we rotate the polarization axis of the analyzer crystal to an arbitrary angle. So if we rotate this crystal to, say, 30 degrees, then we're rotating the polarization axis to 30 degrees from V. And then we have some unknown or arbitrary state. And then to calculate the probabilities that one detector or the other will click on a given trial, given the polarization axis, we just rotate the entire picture I showed before. So we have the projection of the psi vector onto the polarization axis, which has value A, and we can project that onto the other complementary axis, which is B, and A squared plus B squared is 1, and A squared is the probability, and B squared is the other probability. So that's how the mathematics works. If you don't follow that all, don't worry about it. Just keep going. Okay, so here's a poll question. Put up the question, please. Okay, that's good. 50-50, yes, that's right. 50-50, okay. And that's correct. So time is getting short, so I'm just going to discuss the next one with our poll. So we can also do the similar thing if we're in V and we analyze it with the AD rotated crystal, we're again going to get 0.5. Okay, so you have that idea there. Now, here it is. I put up a poll question for this one. Okay, here we have a nice mixture, a 50-50 mixture of answers A and B. Okay, C is not relevant because we're talking about single photons, so we can't really talk about classical light, so that's a red herring. But A and B are equally reasonable, okay? Now, the fact is that if you have a single photon, you could put it through an HV analyzer first, or you could put it through an AD analyzer first. And then that means you're measuring whether it's you're forcing it to decide if it's HV, or if you instead you put it through an AD crystal, you're forcing it to decide if it's A or D. Okay, but if you put it through the HV crystal first, let's say it comes out H. Now you put it through the AD crystal. We already said that if you do that, you're going to get 50-50 chance of coming out A or D, which means you really got no new information about the photon, what state it was before you put it through the HV analyzer. On the other hand, if you put it through the HV and it goes down, that means it's V, the other one. You put it through the second crystal, again, you're going to get 50-50 chance. So you get no new information by putting it through the second crystal. So let's show the poll question again, Brigia. Yeah, that's correct. So most people changed their mind and said no, the first polarization measurement would change the state. That's correct. And so you really can't measure both. I mean, you can do the experiment, but it doesn't actually measure anything more than just putting it through one crystal. So that's the idea that a qubit can only carry one bit of information. It can tell you the answer to one yes or no question. That's one bit. It cannot carry more than one answer to a yes or no question. That's why it's called a bit. Okay, so another subtle point here is that if I have a D oscillating a photon like this on the left-hand side, and I just perturb it a little bit, so the plus 1 over root 2 becomes a minus 1 over root 2, the probabilities for H and V don't change. They're still 1/2 each, but now the oscillation is now tilted to the A direction. Just by changing H to minus H, you've changed the state completely, because you could distinguish those two states by using an AD analyzer crystal. So a small change can lead to a large change of the state. And this effect is called decoherence, which can lead to errors if you're not careful. So it's a case where the probabilities don't change, but the state did change. Okay, I'm going to hand it over now to Francesca, who's going to carry on with part 2.
Sure. Do you want to take a 5 minutes break?
Yeah, maybe 5 to 10. But everybody get back in 5 minutes and we'll start
Sure.
again. And we can answer questions during the break if anybody wants to.
Yeah, so there are a couple of leftover. So there is maybe Belisha, because there are some people who are concerned about getting the recording. So probably they're gonna receive who's registered is gonna receive probably an email through CQN, or is gonna be on the recording on the CQN website. I don't know, Mike, if you know, or
Yes,
maybe
that's correct.
knows. Yeah. Okay.
You don't see my calcite. Oh, there it is. There's my calcite
Yeah.
crystal. Yeah. And what a calcite crystal does is it splits. I didn't try this before. Let's try this during the break. Does it split into two? Yeah, look at that.
Yeah.
See, I really have only one line there, but this is a magic trick. And when I put it through the calcite crystal, it splits into two lines. That's because the light coming through my window it has polarizations, both H and V. And so when it reflects back from the piece of paper, it splits into the H and V. And if I rotate it, it does the same thing. Yeah, cool. Any other questions?
There are a couple of questions about the measurement of this AD and HV polarizer. Janavi asked if we can keep the polarizer so thin that the photon doesn't feel its presence.
Yes. Well, then nothing happens. That's right. That's
Exactly.
right. it would be that the splitting would be so small that the two different portions wouldn't be separated. But if the crystal is long enough, that they start to separate. So that's why a very thin crystal would not make a measurement. Actually, a crystal by itself doesn't make a measurement, as I said. If a photon goes through the crystal and then never hits a detector, but just gets split into two paths, and those paths go indefinitely out into outer space, the single photon is still in a superposition of both paths. It's only when you put a detector or some physical object that acts like a detector that the photon now is forced to decide which path it's in. And once it's decided which path it's in, it stays in that path. Because if you measure path again, it'll be in that same path. Although if you put it through another crystal, rotate it, it'll be split again into two paths. Single photon is split.
I will start sharing my screen.
Yes, go ahead.
Um,
Okay, let's go ahead and get started then.
Yeah. Okay, welcome back. So we will start now part 2, and we will talk about entanglement and encoding of quantum information. Okay, so we have seen with Mike what classical information and bits are, what differentiates bits from qubits. We have seen what superposition is, and we have focused in particular on photons and polarization of light. Now, in part 2, I will explain what entanglement is and what are entangled qubits. We will see how we can create entangled photons in the polarization degree of freedom. So we will focus always on the polarization degree of freedom. And we will start to talk about communication systems, quantum communication, and how to encode quantum information qubits in photons. Okay, just a small recap slide. We have seen what, with this switches picture, what a qubit is. So a qubit can be in 0, 1, or in a superposition of 0 and 1 with this x0 plus y1 with the coefficients. We have seen that measuring the qubits gives either 1 or 0, which is true randomness. So this has been done with one qubit, this x0 plus y1. So now it's natural to ask ourselves what type of states we can create with two qubits now. So let's try to add more qubits to the equation, 2 qubits or even more qubits. We can have a combined state of 2 qubits, for example, here. So we have example qubit A and qubit B both are in the on position. So in this case, we will have a combined state 1, 1. And in this case, the combined state, we will represent it with this ampersand sign. But we can also have a superposition of 2 combined states, and this is what we will refer to as entangled state of 2 qubits. So for example, these 2 parts, 2 combined states in the superposition will be, for example, both of the switches on, 1, 1, in a superposition with both of the switches off, 0, 0. So entanglement, we can define it as a superposition of combined states. But let's see what happens when we measure an entangled state. So we have a state which is a general entangled state of 2 qubits with our coefficients x, y, w, and z. So we have x00, y01, w10, and z11. So what happens when we measure both qubits? We could end up with both switches in the off position, so 0, 0. So here we will focus on the part x00. This is the state that we will get. We can reset the state and make the measurement again. And this time we will end up with both switches in the on position. So in this case, we will have 1, 1. We reset again, next time we could have 0, 1. So first switch in the 0 position, second switch in the 1 position. But we can also have the reverse case. So the first switch now is in the on position, the second switch is in the off position. So this is a 1, 0. Now, the question here is, if we do reset the state again, but we don't measure the qubits, what is the probability to obtain 0 for qubit A and 1 for qubit B if we measure them both? Is it 1, so is it a certainty? Is it 0, or is it y squared? Thank you, Belisha. So we can take a couple of seconds to answer this question. Okay, we can pull up the results. Good. So 78% of you answered y squared, which is indeed the correct result. It does work similarly, so it follows Bohr's rule, so it does work exactly as the case of 1 qubit. So in this case, the probability to observe 0, 0 is x squared, 0, 1 is y squared, 1, 0 is w squared, and 1, 1 is z squared. So we do follow the coefficients that we have in this superposition, and in this case, it was 1 squared. Now, another question is, imagine you measure qubit A and you obtain 1. What do you expect now from a measurement of qubit B? Do you expect 0, 1, or 50% 0 or 50% 1? We have kind of mixed results here. We have a lot of you that said 0 and 1 with equal probabilities. Some of you said 1, couple said 0. Let's see what the correct answer is. And in this case, the correct answer is B, which is we obtain 1. So the reason we obtain 1 is that we have measured qubit A and we obtained 1. So we are in the situation which is highlighted by this red arrow. There is no cross terms in this state. We don't have 0, 1 and 1, 0 anymore. We only have 0, 0. So both of them are 0, both of them are off, or we have 1, 1. So both of them are on. The state is in a superposition of these two possibilities. So if one of the qubits gives us 1, we can infer that the other qubit also is 1, because there is no 1, 0 result. Okay, so this is kind of the switches picture. Now let's try to move on to photons and see what entangled states are when we use photons, and when we use especially photon polarization. So Mike has explained to you what polarization is. We do associate typically the 0 logical state to the horizontal polarization, the 1 logical state to the vertical polarization. And now a pairs of photon A and B can be entangled. And in this case, the state will look like you see here on the slide. We will have XHH, YHV, WVH, ZVV, which is exactly the analogous to the 00, 01, 10, 11 that we have seen with the switches. So in this case, XHH, we have both of the photon in the horizontal polarization. And then we can have HV or VH, which are the cross terms. So we have one photon which will be horizontal, the other vertical, and vice versa. And in the last case here, the blue case, we have both photons in the vertical polarization. So this is how an entangled polarization state of two photons looks like, mathematically at least. And now, I'm going to mention this because typically, we use this for especially useful entangled states, which are called Bell states. And in the polarization degree of freedom, they look like you can see here on the slide. So we have this HV plus or minus VH normalized by 1 over square root of 2. And we also have this HH plus or minus VV, always normalized by square root of 2. So this is what we call Bell states, polarization Bell states, and we will see more of them, especially in part 3, when we will talk about applications of photon entanglement. Okay, so Belisha, here I'm going to ask you to pull up question 13 instead of the following one, because I moved the slide around a little bit. So in here, the question is, we give to Alice and Bob this combined, this entangled state XHH plus YVV. And then we separate Alice and Bob with a certain distance, let's say a long distance, 10,000 kilometers. Imagine that at noon, Alice observes qubit A, and she sees that it has value H. Now the question is, at what time does Alice know the state of qubit B without, so the state of qubit of Bob, without observing the qubit? Is it immediately? Is it never? Or at noon plus the time it takes light to travel from A to B? And let's let's give at least 15, 20 seconds to this one. Okay. You can put up the, thank you, Alicia. Okay, we have a lot of people that said at noon. 20% said at noon plus the time it takes light to travel from A to B. And the correct answer was immediately. So again, this is analogous to what we saw before with the switches. We have a HH plus VV. We do not have cross terms. It's exactly what we saw before with the switches when we had 0, 0, plus 1, 1. If we only have the possibilities of measuring HH on one side or VV on the other side, basically, if Alice knows that this is her state, the state that she shares with Bob, she knows that when she measures H, she knows that Bob also has H. So she knows the state that Bob has because we do not have this cross terms in this case. And Belisha, here, if we can pull up question 14. This question is similar, but it's a bit trickier. We still have the same combined state. Alice still observes at noon that her qubit has value H. Now the question is, at what time does Bob, not Alice, know the state of his own qubit, so of qubit B, without observing it? Again, is it immediately? Is it at noon plus the time it takes light to travel from A to B? Or is it never unless Alice tells him what she observed? And we can pull up the results. Okay, so 63% of people answered never unless Alice tells him what she observed, which is the correct answer. Indeed, when Alice measures her qubit, there is no observable change in Bob's local system. So entanglement does not enable faster than light communication. There is no instant local change on Bob photon, even if they're separated by thousands of light years. They cannot use entanglement to communicate faster than the speed of light. So this is very important. I think it's a common misconception, as Mike said at the beginning. And I hope this poll question cleared it a little bit. We will also see this concept of Alice and Bob needing to communicate in part 3 when we will talk about quantum state teleportation. But I think this is a very important concept to understand. Entanglement does not enable faster than light communication. So Alice needs to pick up her phone, call Bob, and tell Bob what results she had for Bob to know, okay, maybe then I also have H. So this is, I hope I managed to convey a little bit what entanglement is, how entanglement works. I wanted to explain how we can create entanglement, how we can create we will start with photon pairs, and then we will move on how to create polarization entanglement in the lab with how do we do in the lab, or at least one way of doing it in our quantum optics lab. We will talk about a process that is called spontaneous parametric down conversion. And spontaneous parametric down conversion works in the following way. We have one pump photon, we call it pump photon. In this case, it's a blue photon. And this photon will will pump a nonlinear crystal. So what happens is that in a very small probability, this blue photon, this pump photon, will be down converted into two red photons in this case. We call it down conversion because the energy of the two generated photon is lower than the energy of the photon of the parent photon. And this is because we still have to, of course, satisfy energy conservation. So we have that the energy of one blue photon is equivalent to the energy of two red photons in this case. And this is why we will call it down conversion. Now, with spontaneous parametric down conversion, one high energy photon is converted into this two low energy photon. The probability that this happens is very, very small. We're talking about one photons every 100, every 1,000, every 10,000, depending on how strong our pump is, how strong our nonlinear process is. So only a very small part of this photon is going to get down converted. So how do we know if our down conversion is successful? How do we know that the photons are present? We do what is called heralding. So what we do when we pump with our blue photon, we place a detector in one arm and we wait for a click of the detector. So we wait for the detector to tell us that a photon is present. So if one photon is detected in one arm, we know that the twin is in the other arm. And this is referred as to heralding of a single photon. So how do we create entanglement with this spontaneous parametric down conversion process and with these nonlinear crystals? In here, I will use photons as these small red balls. And we can have vertical, horizontal, diagonal, and anti-diagonal polarization, as Mike also explained in his part one. So typically what happens is that a nonlinear crystal will accept for the down conversion only one specific polarization. So for example, let's say that we're sending a photon with a horizontal polarization, so this nonlinear crystal will down convert it into two horizontal red photons. We can also decide to rotate the crystal. And now in this case, we can send a vertical blue photon, and the result of the down conversion is going to be two vertical red photons. So in here, the important point is that each crystal, either the non-rotator or the non-rotated and the rotated version, will accept either horizontal or vertical for the down conversion. And what I mean is that the rotated crystal, the one on the right here, will not accept the horizontal blue photon for the down conversion, of course. And the non-rotated crystal here will not accept the vertical one. So the question here is, poll question number 12. What is the polarization state of the pair of red photons given the situation of the picture here? So the situation of the picture is the following. We are sending a blue photon, but this blue photon is polarized diagonally. And we are stacking two crystals, one rotated, one non-rotated, and one rotated. So what do you expect to see at the output? Do you expect to see no red photon pair produced? Do you expect to see a combined state DD? Or do you expect to see an entangled state HH plus VV with the 1 square root of 2 normalization? Okay, so 56% expect to see an entangled state. We have a 22% of people that expect to see no red photon pair produced, and some 17% combined state DD. So the correct answer is C, which is we're going to produce an entangled state HH plus VV. And I will explain why in a second. Okay, so to understand why we're generating an entangled state HH plus VV in this configuration, we have to recall what is a depolarized photon. So a depolarized photon can be seen as a superposition of H plus V. So it's a photon in a superposition of H plus V. But we do know how H and V act on these crystals. So the H polarization will act on the non-rotated crystal and will generate two horizontal red photons, two horizontally polarized red photons. The vertical polarization will act on the rotated crystal and will generate two vertically polarized red photons. So the pump is in a superposition. The output is going to be in a superposition of this combined state HH plus VV, which is a polarization entangled state. So it is a polarization bell state. And this is why this kind of configuration generates for us a polarization entangled state. So this is one way of generating a polarization entangled state in the lab with photons. Okay, now that we know a little bit more about entanglement, about how photons are generated in the lab, can be manipulated to create polarization entangled states, etc. Let's move to, let's try to start this quantum communication part. Let's talk about communication and encoding. What is a communication system? So we will try to understand here in this following hour, 2 hours, how we can use quantum information and entanglement to communicate, especially from a quantum communication point of view. So what is a communication system? What are the goals of communication systems? The goal of a communication system is to transfer information through a channel. So typically, when we think about communication system, we will have a message source, we will have a sender. A message will be a series of symbols. It can be letters, it can be 0011, so bits. And we will have a receiver that will receive our message and symbols. We will have this communication channel. This communication channel will be typically impacted by some noise source. And we have many different types of communication channels, all the way back to smoke signals that used the density of smoke or the color of smoke to communicate. We can have radio. Radio is a form of communication. We can have telephone, which is still a type of communication, and the communication channel goes through wires. So many different types of communication, many different types of messages, many different types of channels. And communication systems can be used for classical information. So we will deal with classical networks. For example, networks of computers connected by cables or connected by optical fiber links. But we will need dedicated different type of communication systems for quantum information. And in this case, we will talk and we will deal with quantum networks. So quantum networks will be networks of quantum objects, which is photons, ions, atoms. And these quantum objects are going to be connected by entanglement links. So a communication network is defined as a network of entanglement links and nodes that share this quantum information. Quantum information we have seen is a type of information that is encoded in quantum states of physical objects. So we have seen the example of polarization. So to create a quantum network, really the building block is this entanglement link between two nodes. So we will have, for example, this state, polarization Bell state HH plus VV, and we'll need to separate the two nodes by a given long distance, which can be 10,000 kilometers or more. And of course, to create a dense network like the internet that we have today. So to create a quantum internet, we will need many, many nodes, many different types, many different connections, many entanglement links. So before moving to quantum information encoding, I wanted to make clear this part of physical encoding of information from the classical point of view. So if we do have this message, so we have a message source and we have a message, and our message is, for example, 0110 that we are used to, because nowadays we're used to thinking in terms of bits. I want to send this message through a channel, and let's say that my channel is an optical fiber, but an optical fiber doesn't know what is a 0 and what is a 1. So how do I send, for example, a sequence of 0 and 1 using light? I need to choose what I refer to as physical encoding. For example, if we use an electrical signal, even the electrical wire doesn't know what is a 0, what is a 1. But we indicate as 0 the 0-volt line, and we indicate as 1 the plus 5 volts line. And it's an arbitrary choice. We can choose something different. Some people use 3.3 volts. It is up to us. The important thing is to be consistent with this choice when we decide to communicate. For example, for light through an optical fiber, we can encode 0 and 1 using this on-off keying method, which is in a given time window, our 0 is the absence of light and our 1 is the presence of light. So we have a dark and a bright state to indicate our 0 and 1. And again, this is not the only choice possible. There are many, many different choices on physical encoding in optical fibers, with light, with electrical signals. It is not a unique choice, and the same binary message can be encoded in many different ways. And again, the important thing is that we are consistent and we know in which way in which sense we are encoding the information. So we will see later that this still stands for quantum information. So to send quantum information, we have seen that I need a quantum network. This quantum network is going to be made of entanglement links. And here we have then two questions that arise. The first one that we will answer now is, how do I physically encode the qubits in our physical system, so in our photons? And the second is, how do I distribute entanglement to many different locations to create the network? And we will see the answer to these questions later. So for what is encoding, so what is an answer to the first question, qubits can be encoded in many different ways, exactly as in classical communication, in classical information theory. We can use many different supports. We can use many different physical systems. We can use ions. We can use electron spin states, photons, etc., etc. Typically, we talk about stationary qubits, for example, superconducting qubits or electron spin states. And these are most used to store quantum information. So they will become a quantum memory that Mike will talk about in part 4. The photons are typically referred to as flying qubits because they are typically used to transmit quantum information. So we send them through optical fibers. We already have the infrastructure, so it makes sense to use photons for everything that is transmission long distance. And for photons, we can use polarization states, so we can use polarization encoding, we can use photon frequency, we can use time beams, which is the time of arrival of the photon, we can use photon beam path. So encoding, for example, in location, which is the photon beam path encoding, is done in the following way. We have transparent glass waveguides. For example, an optical fiber is a type of waveguide, or you have typically these crystals who are optically carved to create these really guides for photons, guides for light. And we have two possible guided paths. So we have the left one and the right one. So our encoding in this case is that if the photon is present in the left path, that's a logical zero, that's our zero. If the photon is present in the right path, that's a one. Again, that's arbitrary. We could have done it the reverse. We could have said that left path is one, right path is zero. The important thing is to be consistent. So in this case, we choose left path zero, right path one. We can encode in time of arrival. So when the photon is with respect to time and with respect to arrival to the detection. For example, we can have a zero, which is an early photon. It arrives first at the detector stage, or we can encode at a later time. So that would be our one. So in this way, we use time to encode information. So our 0 and 1 in this case is the time of arrival of the photon, so where the photon situates with respect to time. So this is a 0 state, which is early, and a 1 state, which is late. But we can also have superposition states. We can have x0 plus y1. So we can have a superposition of the photon being in an early time and a late time, exactly as we can have a superposition of the photon being in the vertical or in the horizontal polarization. Even in the time being encoding or even in the path encoding, we can identify entangled states. So an example here is that the state 0, 0 plus 1, 1 in the encoding, in the time of arrival encoding is going to be identified with early, early plus late, late. And this is an entangled state in the time of arrival encoding. Again, we can encode using photon polarization, which is what we have seen and what we will focus on during the next part. So we have seen that polarization can be oriented vertically and horizontally. And we have seen that our 0, in this case, is the horizontal polarization, and our 1 is the vertical polarization. Again, we can identify superpositions. For example, the diagonal polarization is going to be a H plus V with 1 over square root of 2. And we can have entangled states in polarization that we have seen. So again, we have many different ways of encoding quantum information. We need to pick one that benefits us because each different encoding will have his pros and cons. So we typically pick an encoding which is good for us, good for our experiment. Now, to kind of conclude this part, there is this poll question, which is about encoding. And here we're using both the polarization encoding and the photon beam path encoding. And the question, this is a bit tricky, I would say. So we do have a photon, which is polarized diagonally. We know that the horizontal polarization is a 0. We know that the vertical polarization is 1. But we also have two waveguides. And this diagonally polarized photon is in the upper waveguide. And we do identify up with 0 and 1 with down. And so the question here is, what qubit state is encoded in this single photon? Is it 0? Is it a superposition of 0 and 1? does it depend on the encoding? And you can take maybe 15 seconds, 20 seconds to answer this one. Okay, so in here, most of the people, 53%, answered B, a superposition of 0 and 1. We have roughly 30% that said it depends on the encoding, and some of you said 0. So the correct answer is that it depends on the encoding. The reason is that depending on the encoding that we choose, these can be either a superposition of 0 and 1. So people who answered B, they are correct if we use the polarization encoding. And likewise, people that answer 0 are correct if we are using the path encoding. So we always have to identify our encoding when we decide to use photons to send quantum information. If we do choose the path encoding, the photon is clearly in the upper waveguide, so we don't care about the polarization, particularly of this photon. This photon is in the upper waveguide, and it can be considered a 0. If we use the polarization encoding, what we care about is the polarization of this photon. And in the polarization encoding, this photon is in a superposition of 0 and 1. So the correct answer is that it depends on the encoding, because depending on the different encodings, this is a completely different, identify a completely different state from a quantum information point of view. It's 0 on one side, 0 plus 1 if we choose polarization. Okay, so this concludes part 2. I don't know if there are some questions, Mike, that you wanted to answer in the Q&A.
I think they've all been answered by typing. Although here's one more question that I'll read and try to answer. In all these discussions, we are talking about enforcing or creating a system with certain level of uncertainty, which behaves similarly to a quantum superposition state. But in principle, if we are enforcing this nature of uncertainty, I fail to understand how it is different from a classical uncertainty versus natural quantum system. This is a very good question, because it's really at the heart of the entire subject of quantum mechanics. And there's two levels at which you can answer it. One is that you can do further experiments that will distinguish between these two types of uncertainty. We haven't actually talked about these examples, but let me give an example. Let's say we have a beam splitter, and we have a single photon hitting the beam splitter, and now the photon goes into two paths. Now, classically, you would say it went into one path or the other path. But in quantum physics, you would say, well, it went into a superposition of two paths. Now, your question is, how can we distinguish those two ways of looking at this situation? The answer is, you bring those paths back together again on a second beam splitter. Now, that one path can go through the second beam splitter or reflect from the second beam splitter. The other path can go through the second beam splitter or reflect from the second beam splitter. So now there's two new paths coming out. And the question is, how do you calculate the probability that the photon will be in one of the final two paths after the second beam splitter? I know this is a lot to absorb, but it turns out that if you use the classical theory, you get the wrong answer. And if you use the quantum theory, you get the correct answer. So by experiments, we know, we can verify that the two ways of looking at uncertainty are completely different. But the second level of question is, why is the world like that? And the answer is, we don't know. That's just the way the world is.
Okay, so if there are no more questions, we can take a 10 minutes break and come back in 10 minutes for part 3, which is applications of photon entanglement. We can wait a couple of more minutes and then go.
Yes, I think technically we have 5 more minutes
5 more
from when you
minutes.
said 10 minutes.
That's great. So let's wait 5 more minutes.
Yeah. But if people have questions now, you can put them in the Q&A box and we'll discuss them. There were some interesting questions about Maxwell's equations, which
I
I can
see that.
which I can comment on if anybody doesn't have any other questions. As everybody knows, Maxwell's equations describe how waves, electromagnetic waves, propagate, through space and beam splitters and so on. And the question was, at the level of a single photon, are Maxwell's equations still valid? Which is a very good question, because if they were still valid, you might think that, well, we can predict exactly the solution of Maxwell's equations, therefore there's no uncertainty. But the answer is that yes, we can predict exactly how the wave evolves, but remember, the wave is only a quantum probability. So we can predict the values of the probabilities everywhere in space. But then when you actually go to make a measurement, you're still subject to quantum uncertainty. And this subject is very well developed. It's called quantum field theory. I think we can start again.
Okay, so let's go and move on to part 3, which is applications of photon entanglement. Oh, okay. So again, we have seen classical information, bits. What is on the quantum side, we have seen what is a superposition, what is entanglement, how does entanglement work in some specific cases. And we have focused on photons and especially polarization of light, which is a type of, a way of encoding quantum information in photons. Now we will move on to part 3, where we will have 3 main subjects. And we are gonna move to the side of quantum technologies for part 3. So we will talk about quantum key distribution, which is a problem of quantum cryptography, quantum state teleportation, and entanglement swapping. Okay, the first subject is quantum key distribution. So we talk about quantum cryptography, and as we did many times during this short course, we start from the classical side to try to then see how we can solve some problem that emerge on the classical side with quantum physics. Now, the problem of cryptography is the following. We do have a message sender, which we identify as Alice, and we do have a message receiver, which is Bob. We have our communication channel. We have seen that our communication channel is impacted by noise. But in this case, it is also impacted by somebody that listens to our conversation, listens to our communication. So this, we're going to call it an eavesdropper, that we typically indicate by Eve in these cryptography problems. And this is a problem of how do we do if we want to share a secret message and we don't want anybody to listen to this message. We don't want Eve to snatch our message away and listen to our conversation. We don't want Eve to intercept our message. What we need to do, what Alice and Bob needs to do, is to share an encryption, a method, so a protocol for encrypting and decrypting their message so that only themselves, only Alice and Bob can read them. So let's say that Alice wants to send a message, hi Bob, and for whatever reason, she doesn't want Eve to know, she doesn't want anybody to know that she's writing hi Bob to Bob. So what she'll do is that she will have a pre-shared, and this is going to be important later, a pre-shared secret key with Bob. And she will use this pre-shared secret key to encrypt her hi Bob message, which is in plain text that anybody can read, to what is referred to as a ciphertext. So she will encrypt hi Bob to XFCEOD. Then what she'll do, she will transmit this message to Bob using a communication channel. Now, Eve could be present and Eve could try to snatch the message away. But she will not understand what she's reading because these symbols do not mean anything to Eve. But Bob will be able to understand what XFCOD mean because he will have a secret key that he shares with Alice. So they will have the same secret key to encrypt and decrypt the message. So Bob will take this message and will use the key to decrypt the message and retrieve hi Bob. This is known as a cryptography protocol. It's simply a procedure and it's publicly known. So everybody knows how the protocol works. Everybody knows how this procedure works. There are many different procedures to encrypt and decrypt messages. What's secret, what's only to Alice and Bob is the key. So the protocol is public, but the key is for Alice and Bob. Now, I think the problem here lies really in this pre-shared secret key, because the problem is that Alice and Bob at some point will need to share this key. One way would be for Alice to take the key, go to Bob's house, give Bob the key, but of course this is very expensive. It's not feasible if there are long distances like thousands of kilometers, like now we are communicating in different states. So we might think, okay, then Alice and Bob will need to share the key over the same network. But the network, they don't know if it's secure or not. So Eve might be listening and might try to snatch the key away. So Eve will also be in possess of the key and will use the key to decrypt the communication between Alice and Bob. So quantum key distribution refers really to this solving this problem of for Alice and Bob to share a key and be confident that nobody can intercept it. So we will use entanglement for this quantum key distribution, and we will use, for example, polarization entanglement. So again, just a recap slide, we have our V polarization, our H polarization, 0 and 1, and we focus here on a specific state only with the cross terms. So this state will be HV, X HV plus Y VH. Now, one interesting question is for question 16, if two photons are in the entangled polarization Bell state, so we have HV plus VH with the cross terms. We are emitting this entangled state, we are emitting these photons, we give the A photon to Alice and we give the B photon to Bob. And Alice and Bob are in possess of this HV polarization analyzer, so that they can discriminate the H and V polarization. Now let's say that Bob measures his photon and obtains H. Here is the poll. What will Alice observe if she measures her photon using a calcite analyzer that separates H and V? The answer is B. We have seen something similar even in the last couple of hours. We, of course, will be in this case of V, A, H, B. So if Bob obtains H, Alice will have B. When we have this kind of Bell state, then I will recall you this part because it will be important for the following part. If Alice observes H, then Bob's state will be V. If Alice observes V, then Bob's state will be H. And what we say, we'll say that Alice observing H conditions Bob's state to be V, and vice versa. Alice observing V will condition Bob's state to be H. Now, same question But this time, so they still share this polarization Bell state. Alice will use a HV analyzer, but this time Bob will use an AD analyzer. Alice observes V. Bob uses his AD analyzer. What will he get as a result? And 84% answer that Bob will have 50% probability to observe D and A, which is the correct answer. So when Alice observes V, we already know that Bob's state will be H because this highlighted red part will be what we get. But we must remember that H is by definition a superposition of the D and A polarization. So if Bob doesn't have an HV analyzer, but if he decides to use an AD analyzer instead, he will get as results this D plus A, which is of course 50% probability to observe D, 50% probability to observe A. We will see how these condition quantum states and how these analyzer settings can be used for quantum key distribution to provide security of messaging. Okay, so this is the framework for quantum key distribution. We have our Alice and Bob, which are separated by a certain distance, and we have a source of two photon polarization Bell states, HV minus VH. In this case, the sign is not important. So this source generates a series of identical Bell states. So you will generate many of these Bell states, and Alice and Bob will choose their measurement settings. So they will choose to pick either the HV analyzer or the DA analyzer for however many tries they will receive, however many photons they will receive. So again, for the state, if Alice observes H, Bob will have V. If Alice observes V, then Bob will have H. But an important thing to mention is that this Bell state can be equivalently written. So really from a mathematical perspective, it is perfectly equivalent to the state dA minus AD, normalized over square root of 2. So in this case, if we look at the state, how it's written like that, and we measure with a dA analyzer, if Alice observes D, then Bob's state will be A. And if Alice observes A, then Bob's state will be D. So again, it's important to understand this is the same state. The HV minus VH and the dA minus AD, it is the same state. It's just written in a different way. And we will pick the mathematical form that is more convenient for us to do the calculations or when we measure, for example. Okay, so this source will give Alice and Bob this polarization entangled state. Again, in orange, we have the HV basis. In blue, we have the writing of the state in the dA basis. And then the protocol works the following way. So Alice and Bob will randomly switch their analyzer setting between HV or DA. And what I mean is that they don't tell anybody what settings they're using. They just completely randomly choose. Alice doesn't tell Bob what settings she's using. Bob doesn't tell Alice. They really pick the settings HV or DA randomly. So they keep this secret, but they keep track of the settings that they're using. So they write it down on a notebook. And they keep track of the results. So let's see what happens. Let's say that randomly Alice picks HV and randomly Bob picks HV. So they don't know what settings, Bob doesn't know what settings Alice has picked. Alice doesn't know what settings Bob has picked, but they randomly picked both HV. So Alice will have H as a result, let's say, and Bob will have V, which makes sense because if we look at the orange state here, we see that if Alice gets H, Bob needs to get V, and vice versa. When Bob has V, Alice needs to have H. So this does make sense, and we will use it later. So we do a second try. We have same polarization entangled state, a second one. And now completely randomly, Alice decides to pick the setting DA, so to measure with the DA analyzer. Bob decides to measure with the DA analyzer as well. Again, they don't know that they're using the same setting. And Alice's result is A. So if we look here at the blue state, we realize that when Alice has A here, Bob's result will be D. So again, this makes sense. This is what we have seen even in the previous hours. And now they do a third try. So now Alice picks HV, Bob picks DA. So there is a mismatch between their setting. And again, they don't know. Let's say that Alice's result is HV. So when Alice's result is HV, we know that Bob's result needs to be V. So V is a superposition of DA. Bob is measuring with a DA analyzer, so he has a 50% probability of getting A, 50% of getting D. In this case, he gets A. So this is irrelevant for the purpose of quantum key distribution, so we will not use these results later on. And now fourth try, they still use the DA settings, but this time something weird happens, which is that Alice gets D, but also Bob gets D. And this is an error. It's an error because we know that when Alice gets D, if we look at the blue state, the state, the entangled state, is made in such a way that when Alice gets A, the correlation brings Bob to also have A. So this weird result of both having D and D, it's an error that's potentially caused by an eavesdropper, so somebody that's listening to our channel. So we go on, we do, let's say, 10,000 of these. So they keep noting in their notebook. And let's say that they repeat this 10,000 times. So they do this setting measurement, writing down 10,000 times. So they keep records of what they're doing. So to check if there is an eavesdropper, what they do is that they randomly select 1,000 of these trials. Let's say they say, okay, let's pick 2, 3, 10, 12, 20, until they get to 1,000. And then they share in a public way. So they really share the settings and the results of these 1,000 trials to see if they are okay or if there are mistakes. Now, if there are too many errors, they discard all of the data and they don't use it because they know that if there are too many mistakes, somebody's listening to the channel. If no if is detected, they use the remaining 9,000 trial to create the key. So to create their shared key that they will use later for encrypting and decrypting their classical messages. So they do it in the following way. They do share the settings. So they do share if they have used HV or DA, but they keep the results secret. When there is, for Alice, when there is result V, she will write 1, H will write 0, D 1, A 0. Bob will do the reverse. V is going to become 0, H is going to become 1, D 0, A 1. They will not use the results where there is a mismatch because there is an inherent probability of getting 50-50 in the case of Bob, for example, or Alice, vice versa. And in this way, they will build their shared secret key. So if you look at the first row, they know now, because they have shared their setting, that both they have used HV. So Alice has H. She doesn't share this, but she has H, so she will write 0. Bob now has V, so he will also write 0, because this is what Bob does. When he has V, 0, Alice has H is going to be her 0. So in this way, they build their key made of zeros and ones, following their own secret results. Okay, so the goal, if everything works out, has been achieved. They have managed to share a key in a secure way. And again, they use, in this case, entanglement. They are using quantum physics. They are using an entangled state to be able to do this key distribution, to share a key. The key itself is classical because the key is a sequence of zeros and one, and they will use the key to encrypt and decrypt a classical message which is sent over the classical internet. But the way of distributing this key, of creating the key, has used entanglement. So that's why we refer to as quantum key distribution. We have used quantum physics, we have used entanglement for the distribution of this key. Okay, so now, in this case, they are sharing the key in a quantum way, let's say, but they are sending classical messages. But with quantum communication, we can also ask ourselves, is there a way to transmit quantum states from over long distances? So not classical states, but quantum states. So in this case, we will have Professor Xavier, for example, that wants to send a quantum state to Bob. Of course, we have no quantum telephone, so we will have to find a different way of sending a quantum state. So let's say, for example, okay, we want to transmit the state of a photon, so we want to transmit the quantum information encoded in the photon. And we can think about, okay, well, a photon, we can just send it with an optical fiber over to Bob. We don't care if Bob is 10,000 kilometers apart. We just have an optical fiber connecting Xavier and Bob. We take the photon, the quantum information encoded in the photon, and we send the photon through an optical fiber over to Bob. Now, the problem here is loss, because after 100 kilometers, for example, only 1% of photons is transmitted. This means that in this distance, we are losing 99 photons when we send 100 photons, which is a lot. This is for 100 kilometers. If we go to 1000, it's even worse. Basically, no photons will arrive to Bob. So we can ask ourselves if classical communication can help to solve this problem, because we use fibers in classical communication. We have loss in classical communication. Maybe classical communication can help us mitigate the losses or solve our problem. So again, also in classical communication, losses attenuate the system. And what we can do, if we have a classical signal, the classical signal will get weaker and weaker if it propagates over a long distance. But then we will place amplifiers along the fiber to be able to amplify the signal to its original intensity. So this way we can mitigate the losses. Let's say we can solve the problem of the losses in classical information. Now, can we do something similar for quantum information? Can we use a quantum amplifier to amplify quantum information in our photons? Turns out that we can't, because it's not allowed for us to make a copy of an unknown quantum state without destroying the state of the original object. So we can't amplify quantum information as we would do with classical information. We can't copy qubit states. We can copy arbitrary unknown qubit states. So we have to find a different way of solving this problem of transmitting a quantum state. Obviously, we can't transmit it like we would do with a classical signal, because we would lose all of the photons. So the way we do to transmit quantum states over a long distance is to use quantum state teleportation. So in here, I will give a sketch of quantum state teleportation. I will explain it later, but I just want to point out two things that are going to be very important for quantum state teleportation. So quantum state teleportation works this way. We have a Professor Xavier who's sending a quantum state. We have Alice who's going to help Professor Xavier. Bob has to receive the state. And two central pieces of this protocol are this joint measurement tool, which is a tool that measures the photon of Professor Xavier and an entangled pair that's gonna be given to Alice and Bob. And again, the entangled photon pair, which is a shared entangled state between Alice and Bob. And this is also a problem that we need to solve, because if we want to connect Alice and Bob, or Xavier and Alice and Bob on the other side over long distances, we also need to find a way to distribute this shared entanglement. So let's begin with the joint measurement tool and see how it works and how this joint measurement tool can help us. So the joint measurement tool is a tool, or also called Bell state measurement. It's a tool that gives information about a pair of photons, not about each individual member. So for example, if we have a polarization Bell state, we send the two photons through the joint measurement tool, and then we will have an outcome. And the outcome will tell us what polarization Bell state we have between the ones that we can see here on the right. So between HV plus minus VV and HV plus minus VH. Now, in many cases, the joint measurement tool is not perfect, but we can retrieve partial information about the pair. So in this case, instead of knowing what exactly polarization Bell state we have, we can typically know if the polarizations are the same or if they are different. And what I mean is, if they are the same, we will have this state HH plus minus VV. So the polarization of Alice and Bob in the combined states are the same. So HH in a superposition with Alice having V, Bob having V. Or if they are different, for example, we have, again, HV plus minus VH. Now let's see how this tool works in the case of entanglement swapping. Entanglement swapping refers to the goal of using this joint measurement to entangle two distant photons that have not interacted. So we start with two separate Bell pairs. We have an entangled state of A and B, so HV plus VH, and we have an entangled state of C and D, so HV plus VH again, but for C and D. So we have four photons. And it's worth to note that A is not entangled with C or D. A is entangled with B, C is entangled with D. Now, what we're gonna do is we're gonna take the B and C photon and we're gonna send it to the joint measurement tool. And then we're gonna read out the outcome. Is it the same, the polarization, or is it different? So let's do an example, and let's say that the joint measurement outcome is that B and C are the same. So they have the same polarization. And our question is, what is the state that A and D will end up with? We have two possible cases. If B and C, the polarization of B and C are the same, we can have that they are either V, so B is V, C is V, or in a superposition with B is H, C is H. So if we take the first case, for example, we take the two entangled state here, A, B, C, D, and let's say that the two polarization are both V. So we have VB, VC. As we can see here, if we select B and C as being V, then A and D are left in the H polarization. But of course, this case is in a superposition with the case of B and C being in the horizontal polarization. So if this happens, as you can see here, we are left with A and D being in the vertical polarization now. So the final state is HH plus VV, as you can see here from what has been left. Of course, normalized with square root of 2. So what we see here is that A and D now, the photons A and D, are in a Bell state. So they are entangled even if they have not interacted. So in a way, this joint measurement tool has transferred, this Bell measurement, joint measurement tool has transferred the correlation of the A, B, and C, D states to the A and D photons. Okay, so now let's imagine poll question 18 that we still have the same A, B, C, D states, but now the outcome of the joint measurement is that B and C are different instead of being the same. What do you think is the state created for A and D? And maybe we can give 30 seconds for this one. Okay, we can maybe pull up the results. Okay, so we have 50% said answer A, 26 answer B, 12% answer C. Let's see. And yeah, most of you got the right answer. Let's see why this is the right answer. So we proceed exactly in the same way as we did if the B and C outcome was the same. So we isolate the different polarization for the B and C case instead of same polarization. So again, we have two possible cases which are going to be in a superposition. We have the case of B and C being H and V, but we also have the case where B and C are V and H. So in this case, B is V, C is H. So in the first case, we see that when we isolate B being H and C being V, we are left with A in V in the vertical polarization and D in the horizontal polarization. Now, this is in a superposition with the second case where we have VB and HC. And when we isolate this, we are left with HAVD. So the final state will be VAHD in a superposition with HAVD normalized over square root of 2. So again, it is still a Bell state. It is still a polarization entangled state. It's just different polarization entangled state. So A and D will be left entangled in a different way with different types of correlations that in the case of B and C being same. Okay, so now that we have seen kind of how it works, the joint measurement, so that it can transfer these correlations, it's a powerful tool. Let's take a look at how quantum state teleportation works. Now, for quantum state teleportation, again, the goal is to is to send a quantum state. When I say send a quantum state, we really want to send the state xh plus yv or x0 plus y0 from a quantum information logical state perspective. And I want to point out that here the coefficients x and y are arbitrary coefficients. So we don't know which coefficients they are. We want to send exactly this piece of quantum information with x and y being arbitrary. Now, Xavier wants to send this photon, this state, to Bob without, of course, sending the photon directly to Bob. And we have seen why, because he knows he will simply lose the photon in the optical fiber if Bob is very distant. So what Professor Xavier does, he will ask for Alice to help. And they decide to get an entangled photon pair. So this entangled state, HV plus VH, we will send half of it to Alice. So Alice will get the A photon and half of it to Bob. So Bob will get the B photon. And then what they do is that Alice makes a joint measurement on Professor Xavier photon and her part of the entangled state, so the A photon. And then she will read the outcome. And something not really the same as in entanglement swapping, but something similar will happen, which is that the state of Professor Xavier will be transferred to Bob's photon on the condition that Bob applies a specific state transformation. And the specific state transformation on his photon that Bob has to do, he will need to ask to Alice. So what happens is that Alice needs to call Bob. So this is a classical message. So she will just need to communicate classically with an email, with a phone call. And she will have to tell Bob what is the outcome of the joint measurement. Without this piece of classical information, Bob cannot know what specific transformation to apply to his photon B, to retrieve exactly the state that Xavier had. So in here, there are a couple of important points to point out. The first one is that Alice never knows the state. The second is that the photon of Professor Xavier does not exist anymore. It has been measured by Alice in the joint measurement, so it has been destroyed. The joint measurement is a destructive measurement. But Bob will get the state, which is the important thing. So when we say quantum state teleportation, really we don't. It has to be clear that the photon of Xavier hasn't obviously been teleported to Bob. The photon of Xavier has been destroyed in the joint measurement, but the state is in Bob's hands now, which is what we wanted. We want Bob to have the state. We don't care if Bob doesn't have that specific photon that was in the hands of Xavier. Last important thing to point out is that this is not instantaneous. So again, we see we can't use this entanglement. We can't use this for faster than light communication. Bob needs to wait for Alice call to implement the specific state transformation on his photon. Without Alice call, he can't retrieve the original state. And of course, the Alice call is not faster than light, of course. It is limited by the speed of light. Therefore, this type of communication is not instantaneous. It is still limited by the speed of light because Alice needs to communicate classically with Bob. Last point of this quantum state teleportation protocol is concerning this entangled state. So this entangled state between Alice and Bob, how do we give to Alice and Bob an entangled photon pair without losing the photons? So basically, we risk of going back to the original problem. If we send the photons simply through the entangled states, simply through optical fibers, if Alice and Bob are very far away, this entangled state will be lost before reaching them. Either one photon or both of the photons, it's going to be very complicated. So the last piece that we need, that Mike will talk more about in part 4, is how to distribute this entanglement over long distances if Bob and Alice are at a long distance. And we have kind of seen a tool that can help us, which is entanglement swapping. So what we need to do if we want to give to Alice and Bob this resource, this entangled state, is to break the distance between them into small sections. So the photons will not need to cover the entire distance between Alice and Bob. It will just need to cover an intermediate distance just to go over to the next yellow dot here, the next joint measurement. So we need to have many entangled pairs and many intermediate stations. The requirement here is that this joint measurement will need to be successful exactly at the same time. So we have seen that when we have a joint measurement on a B and C photons and we have two entangled pairs, this joint measurement will entangle the photons that had never interacted. So in this case, we will have A and D entangled, and then we can propagate the chain this way. So for this to work, we need this joint measurement to be successful and to happen at the same time. So we need these measurements to be synchronized. And these will help us establish an entanglement link between Alice and Bob. Now, the problem here is that the probability of success of all of this chain of joint measurement doesn't scale very well if we have a lot of intermediate links. For example, the protocol in many cases will fail because these entangled photons are not generated at the same time. We have seen that entanglement generation or photon generation is probabilistic if we use, for example, spontaneous parametric down conversion. So a lot of time this generation will fail. And this will impact our synchronization. So in a lot of cases, we will have some joint measurement. Here they're indicated as Bell state measurements, which are not successful. Now, the solution here is to use quantum memories to store the entangled photons. So basically, we will have quantum memories, and we will see it in part 4, in the intermediate station. These quantum memories will store the entangled photons. We will wait for the whole chain to be ready to go. And when everything is ready to go, what we need to do is hit a button of our quantum memory to release the entangled pair. So in this way, we have this entanglement HV plus VH stored in a stationary qubit in a quantum memory. Okay, so quantum state teleportation, just to wrap up what we have seen in this later part, has helped us share this quantum state without sending it physically through an optical fiber with the risk of losing it. And we have seen that we have used this joint measurement tool, this Bell state measurement tool. We have seen how to use entanglement swapping for distributing shared entangled states. And we have seen what the limits are. We are limited by, of course, the speed of light. But this way we can send a quantum state from Xavier to Bob without losing the state. Okay, and I guess we are done with part 3 with these applications of photon entanglement. I don't know if there are some questions.
Yes, let me jump in here, Francesca. Yeah, there were. You can hear me, right?
Sure.
Yeah, there were many questions in the Q&A which I answered in writing. But let me, if people are able to sit here, you can go take your break if you want, and the answers are in the Q&A. But if you want to listen for a second here, let me summarize the answers. The questions were all about first of all, how do Alice and Bob know that they're both using the same encoding scheme? They have to know that H means 0 and V means 1, and also D means 0 and A means 1. They have to agree on that in advance. And this is part of the protocol, but this information is publicly known. It's not a security risk. Okay. The second question is, if Eve intercepts a photon and then makes a measurement on it and then sends out another photon to Bob, so Bob doesn't know that Eve intercepted the photon, what's the probability that Bob will see an error? In other words, does Eve intercepting always cause an error? The answer is no. There's only a 50% probability, I think it is, or maybe it's 25%, I forget, probability that Bob will get the correct answer, even though Eve tampered with it, because after all, everything is by probability. So this number is known, this probability is known, and this can be accounted for in the theory. Okay, then the question is, well, if there's a case where Alice and Bob have the same setting, but they get the wrong answers, they get the answers that are mismatched, how do they know that if they don't share the results publicly? And that's actually a very subtle question. As Francesca said, if they run 10,000 trials, what they do afterwards is they take 10% of those trials and they publicly share the results. So this is simply a step by which they can estimate how many errors are there in the total data set. Now, it turns out that if the total percentage of trials that are in error is small enough, let's say less than 5%, then they're still good to go. Okay. So they will still have these errors in their key set, but they know that there's only 5% of errors. So the key is not perfect. So that's the first thing to realize. And so that was a very good question. What happened? What do they do if the key is not perfect? So they now have 9,000, shared key bits, but 5% of them are wrong. They're in error. How can they still use this to encrypt classical messages? Well, the answer is that this is really a question of classical computer science. If you start with 9,000 key bits, 5% of them are in error, but you don't know which ones are in error, what you can do is you can run a classical algorithm, which is called error correction, and it reduces the 9,000 key bits down to, let's say, 8,000 key bits. But at the same time, it squeezes out all the errors with a very high probability. So now with those 8,000 you have left over, maybe the error probability is only 0.0001%. And that very tiny error is not going to really hurt Alice and Bob significantly. And you can squeeze it even more. The longer the data set is, the more you can squeeze out the errors. So this is called classical error correction. And it's really a separate issue from the quantum case. Okay, so there's a lot of classical computer science that goes hand in hand with the quantum key distribution. Okay, very good. So actually, that was our 5-minute break. And I hope everybody is back.
I will stop sharing.
You can stop sharing and I will start sharing. Okay, now let me share. And let's see, let me not do that. I have to go over to Zoom here. Now I can share. Yes, share. Yes, now let me annotate. Okay, do you see my pointer?
Yes.
Yes, okay. Okay, we're good to go then again. So we're now on our final section, which is actually a little bit shorter than some of the previous sections because we've already covered so much material. And I'm sure that you still have a few questions in your mind. In fact, questions were asked in the Q&A chat. The main question is, how do we extend the distance of entanglement sharing? As Francesca said, you can lose the photon at any point from a fiber. It can escape out the fiber, and that would destroy the ability to use entanglement. So how do we extend the distance? Okay, so we're gonna talk about these topics fairly quickly. Okay, so to back up again for a broader perspective, what is a quantum internet? And then how do we build it? So it's a network to distribute quantum entanglement to any two or more locations, regardless of the distance. Okay. And at the same time, it should be interoperable between many different types of quantum systems. Like Alice could be using atoms, like a single atom, like I showed earlier, and Bob could be using, say, a special kind of atom that's embedded inside of a diamond crystal. So Alice is using one kind of atom and Bob is using a different kind of atom. But they have to be able to communicate with each other. And there are many technical issues there, which we won't go into. But ultimately, this is why it's called interoperable. In fact, that's why the internet is called the internet, if you didn't know that. Internet means interoperable network. And finally, third, you need a classical network, like Francesca said. Alice and Bob need to be able to communicate classically at the same time. So they can not only set up their protocols, but they can also share some classical information, like for error detection and so on. And also, of course, in a network, there's always questions of switching. You can see in the background here a complicated network with a lot of different pathways and nodes which have to control switching. So this is still a open research question in both engineering question that's being researched now at the Center for Quantum Networks, which we're both part of. Okay, so just to review what you just learned about teleportation. So Professor Xavier has a state which he may or may not even know what the values of X and Y numbers are, but he wants to get that state of that particle, that photon, over to Bob by just sending it once, sending the state once. Okay, so what they need to have a shared entanglement resource, which could be provided by a third party. Maybe there's this third station inside the network that is sending out these entangled photons, many of them. And Alice and Bob are going to use those entangled photons, A and B, to do their protocol, which is, as you saw, a joint measurement of some sort between the X photon and the A photon with a particular outcome, which tells Alice information about the combined state of X and A, but it doesn't tell Alice the state of A, and it does not tell Alice the state of X. So she takes that information, sends it classically to Bob, and then Bob receives the B photon and then carries out with some kind of a device one of four possible transformations. And these transformations are just essentially rotating the photon polarization in a certain way. You know, it could be vertical, it could be 30 degrees from vertical, it could be minus 75 degrees from vertical. But there are devices you can use to just rotate the polarization. So Bob uses one of those transformations, and then magically, the B photon is transformed into the state X plus Y, which is exactly the same as the state that Professor Xavier had, which was then destroyed in the measurement. Okay, so that's the review. Okay, but now the problem is that the entangled B photon could be lost out the fiber. And of course, the A photon could also be lost. So that's a problem. So what do we do about that? Well, why is there loss? Because glass fiber is made of two parts. There's an inner core, and there's a cladding outside of it. And the idea is that the photons are supposed to reflect internally from this interface many, many times, millions of times. But sometimes the photon is lost out the side, and you never can recover it. And for example, after 80 kilometers, which is not that far, that's the distance between two cities, the power is decreased by 10,000. That means if you send one photon into this end, after 80 kilometers, there's only one chance in 10,000 that photon will survive at the other end. So that's very bad. It's also a similar problem if you send photons to the atmosphere, for example, from a satellite down to the ground. So what do we do? As Francesca hinted, we have this new technology. We need to have quantum memories where Alice and Bob can store the photons. If they do get the photon, they can store it, and then they can release it on demand. That means whenever they feel like it, they can release it. In fact, they could have thousands of entangled pairs stored in these quantum memories, and then they could release them whenever they wanted to. But again, the problem is, how do you get the B photon and the A photon to Alice and Bob over these very large distances? The answer is you use something called a quantum repeater chain. And I'll now explain that. Okay, I first have to explain, though, how the quantum memory works, and then we'll use that to do the quantum repeater chain. Okay, so remember, in an atom, a single atom, like this one I've indicated here in the middle, it has one important electron in it. And that electron can be spinning clockwise or counterclockwise with respect to the vertical axis. Now, it turns out that those two spinning states have different energies. Very small difference of energy, but it's a measurable amount of different energy. Okay, so that's how we distinguish them. And again, we encode a 0 into the clockwise and a 1 into the counterclockwise. That's part of our protocol. Okay. Now, how do we make a memory? This is a bit complicated, but I'll do my best. Okay, so what we have is we have this atom, which is called an ion. It's actually an atom. Okay. And it has these two very closely spaced energy levels. The vertical axis here is energy. So the lowest energy is the clockwise. And if we increase the energy a little bit, then it spins counterclockwise. Okay, now initially the spinning electron is in the clockwise spin state. And there's a laser which we apply to this atom all the time. Well, initially we turn it on and we apply it. It has a certain amount of energy in each laser photon. Now the incoming photon comes in. When that photon comes into this atom, this is what happens. That photon can be absorbed, which means annihilated or destroyed. And then the laser can stimulate the atom to transfer to the clockwise, from the clockwise to the counterclockwise. So this photon is absorbed and the laser emits a photon into the atom. And the difference of those two energies is enough to make up the difference between clockwise and counterclockwise. Okay, for those who know, this is called Raman scattering and was discovered by a famous physicist in India named Raman, who got the Nobel Prize for learning about this phenomenon. Okay, now after this atom has its electron spin flipped to counterclockwise, we turn off the laser. Okay, when we turn off the laser, now the electron is trapped in the counterclockwise spinning orientation, and it cannot get out of there. So it can stay there for many seconds, allowing Alice and Bob to wait however many half of seconds they want, or nanoseconds or microseconds, before they're going to release it. How do they release it? They turn the laser back on. Now the laser loses a photon, and our interesting single photon is regenerated, recreated, and sending the electron from the counterclockwise back to the clockwise, and the photon is now outgoing. So we've basically taken this photon, we've stored it for a while, and we've read it out or released it again. Okay, so that's a memory. It has a synchronization capabilities because the user can wait any amount of time they want between storage and readout. Good. Now, moving on to entanglement. This combines a lot of ideas we've already discussed. Let's say that the photon is in a polarization entangled state, but you don't know the values of x and y. We just know that x squared plus y squared equals 1, but we don't know the actual values. But yet we still want to store the state of that photon in an atom, okay? Actually, what we do is we have two atoms, okay? We have memory atom A over here, and over here, different location, we have memory atom B. We're going to somehow share this photon between the two, okay? So what we're going to do is we're going to use a calcite crystal. That's an HV sorting crystal. So the H component of the photon goes in this path, but the photon also goes in this path, and you have now an entanglement between these two paths. But the state of polarization is still XH plus YV, even though the photon has been split into two paths. Now, this path of the photon goes in this memory and has a certain chance of sending this memory atom A into counterclockwise. But this path of the same single photon goes to this memory, and it has a chance to send atom B into the counterclockwise state. But of course, not both of those can happen, right? If memory atom A is transferred in state, then B is not. And if memory B is transferred state, A is not. However, if we now put two detectors over here and neither detector clicks, that means that the photon has been absorbed and stored in one of those memories. But you don't know, and nobody, even nature doesn't know, the universe doesn't know which of these memory atoms has had its spin flipped from clockwise to counterclockwise. That means that the combined state of these two memory atoms is now entangled. This coefficient X gets transferred onto this amplitude or this state, which is A is counterclockwise and B is clockwise, in superposition with A is clockwise and B is counterclockwise. So we've converted the polarization state of a single photon into an entangled state of two quantum memories. That's, in my opinion, that's pretty cool. Now, let's talk about quantum repeater chains. Okay, so we have Alice over here on the far left, 10,000 kilometers away from Bob. Now, we know we can't just send a photon from Alice to Alice and Bob directly. Okay, so what do? We want to get entanglement between Alice and Bob's memories, memory 1 and memory 4. So what we do is we make a chain of entanglement transfers. We first have a small distance between memories 1 and 2, and we can attempt to do entanglement by the scheme that I just showed, by sending a photon from a third location to a beam through a calcite analyzer, and then the two paths, the H and the V path, to these two memories. As I showed on the previous slide, that's what this dashed line is all about. And so we wait until that works. And now we know that memory 1 and memory 2 are entangled. At the same time, Bob is doing that with memories 3 and 4. And after a while, he knows that memories 3 and 4 are entangled. Okay. Now, the memories might be separated by, 10 kilometers. So you don't have to worry too much about photon loss. You just wait until you find entanglement between those 4. But there's still no entanglement between Alice and Bob, right? So what do we do next? Now, we try to do entanglement swapping, as Francesca described, between memories 3 and 4. We send a photon from memory 3 to the Bell state measurement, or the joint measurement, and we send a photon from memory 2 to the joint measurement, and we get an outcome. So this is sort of like teleportation, but it's not really that. It's really entanglement swapping. So depending on which outcome is reported here, so who's ever in the middle, say a person named Charlie is in the middle, Charlie has to make telephone calls to Alice and a telephone call to Bob saying, aha, I measured these two photons and I got this outcome in my joint measurement. That tells Alice and Bob exactly that they have an entangled state between their two memories, and it tells them exactly which entangled state they have. Remember, Francesca said there are 4 possible Bell states, HH plus VV, HV minus VH, et cetera. There's 4 of them. And this middle person, Charlie, can tell from the outcome, can tell Alice and Bob what entangled state they have. But Charlie actually doesn't know what entangled state they have, but Alice and Bob do, because they know what the original states were. So this is a kind of a subtlety, but only Alice and Bob actually possess the entangled state. Okay, so if you believe that, then you can believe the next level of this. We can just continue this process. The way it's all set up is that there's many nodes, the blue circles, and each node could be, say, in a different city, separated by 10 kilometers. So now we have, 50 or 60 kilometers in total. And each node contains 2 quantum memories, which are right side by side in the laboratory. So what they do is they first try, and again, there has to be, operators or even computer operators at all these different stations. So the first thing you do is you try entanglement between all adjacent nearest neighbor nodes, and you entangle like the right-hand quantum atom with the left-hand quantum atom in this other node. And you keep doing that until everybody raises their hand and says, yay, we have successful entanglement across all these black dotted links. And that might take a while. That might take a few seconds. But because you have quantum memories, you can synchronize everything and store it and keep trying. And eventually, they're all going to say, yay, we have entanglement. Okay, Once that's done, repeat until success, then the local operators, who's ever inside one node, they make a Bell state measurement between their two local atoms. Okay. And they all make Bell state measurements. Now they all have to announce publicly what the Bell state measurements revealed. Which of the four Bell states did they achieve? Did they observe? This information is enough to let Alice and Bob at the far nodes know that they now have entanglement. And notice they did not sacrifice both of their atoms. Everybody in the middle sacrificed both of their atoms, so destroyed their states. But Alice kept one and Bob kept one, and therefore Alice's atom is now entangled with Bob's atom, which again is very cool because those atoms were never in physical contact. They're only in like informational contact. So now they have entanglement across a very large distance. So finally, I'll show this slide here. If we want to make a grid, because we know that the internet is not just one long chain of nodes, it's a two-dimensional lattice covering thousands of different locations. So let's say Alice is in this node here, this location, and she holds 4 quantum memories. Each quantum memory has one atom in it, and she can do that reading and read out scheme. So, and Bob is over here, and he also has 4 atoms. Now, all these other nodes also have, each has 4 quantum memories. Each memory has 1 atom. So everybody starts at the same time trying to entangle their nearest neighbor atom with their nearest neighbor friend's atom. So all these dashed lines here are entanglement efforts. Now they keep trying. Now it's very unlikely that all these links are going to be successful at the same time, because remember, photons can be lost, and you have to be lucky that the photon arrives. Even for 10 kilometers, you can still lose photons, or maybe these are 50-kilometer links. But eventually, if you wait long enough, here's a cool thing that happens. Some of the nodes will succeed in entangling to their nearest neighbor, like here, here, and here. So now Alice is entangled to this node up here, but that's too bad for Bob because Bob is not there. The real goal was to entangle Alice and Bob. So it turns out in this simulation, this one trial, this is a probabilistic simulation. It just turned out that in this particular case, Alice is entangled to Bob by 2 different pathways. Alice's memory labeled number 2 is entangled to Bob memory number 4, and Alice's memory number 1 is entangled to this green line to Bob's memory 3. So they actually have succeeded just by good luck in having 2 entanglement paths. And they can do something with that. Now, if you run this trial again, you'll have a totally different topology here of entanglements. So if you're trying to entangle Alice here with the upper left corner node, you may have to try a different number of trials to get that to work. Okay, so that's how it all works. It's all probabilistic, but again, it's not classical probability. That is entanglement. I mean, the probability for this to work, you can calculate by quantum probabilities, which is similar to classical probability theory. But the whole point of it is that once you get entanglement, you have a quantum resource that can do tasks which would be impossible to do with classical resources. So entanglement is more powerful than just correlation. Okay, so what can you do with it? Well, we talked about a few different things before, just to talk about those again. You could do remote quantum computing. Like if Alice is here, I forgot to draw Alice here, she could communicate with a quantum computer that's 1,000 kilometers away in another laboratory. And she could send quantum information, namely a bunch of quantum states, to that quantum computer. That quantum computer could load those quantum states. It could do a quantum computation, get an answer, which is not to be revealed to the local operators of this quantum computer. Those people are just servants getting paid some money, and you don't want them to know what the answer was. So this quantum computer now feeds back to Alice a bunch of qubits, and she can now read those qubits at her location, and that gives her the answer to the quantum calculation. Whereas the people at the computer operating lab, they know nothing about what the answer was, because if they try to read it, they'll destroy it, and Alice will be angry. She won't pay them any money. Okay. Now the other one is Alice may have a quantum computer herself, and she may want her quantum computer to collaborate with another quantum computer in a distant laboratory. They can perhaps do a computation together, like parallel processing, that couldn't be done by a single computer in the same amount of time. So by teaming up two computers, you might cut the computing time by a factor of 4, for example. Okay, they can, and as Francesca also described, if Alice is over here on the left, she can do a quantum key distribution with Bob. Okay, now the second thing we mentioned earlier is quantum sensors. We won't talk about that in this course, but it's a whole large field. Quantum sensors, what that means. So what is a sensor? Okay, a sensor would be like a seismometer. So here's Earth science or planetary science. A seismometer is a machine that detects vibrations. So if an earthquake happens in some location, the acoustic vibrations in the ground are then picked up by a microphone in somebody's laboratory. And by having many laboratories around the world picking up these seismic vibrations and recording those, they can then do a computer calculation to determine, say, the location of the earthquake. Now, that's a classical technology, which we do now. But if you could actually connect all those sensors with a quantum network instead of a classical network, you could actually improve greatly the ability to analyze the earthquake's location and all of its properties. Another very cool example of that is the following. I wish I had a picture to show you of this. Well, let me see if I can draw a picture here if people are still, where's my annotate? My annotate. This annotate might work. Does this work? Yeah, can you see that, Francesca?
Yes, yes.
Oh, green line. Okay, so here's a very cool thing. What was recently done was people made an image of a black hole. At the center of our galaxy, there's a black hole. And some of you had seen pictures of that. The image looks like a donut or something like that, right? It actually looks orange, but that doesn't matter. How did they take a picture of a black hole, which is at the center of our galaxy? It's so far away. Okay, what they did was they're sitting on the Earth, right? You're sitting on the Earth. They have a radio telescope over here, and a radio telescope here, and a radio telescope here, and a radio telescope here. Now what happens is the black hole sends out light, okay, in all directions. It's actually not light; it's actually radio signals. Okay. Now those radio signals are picked up by these antennas here. All of them are picking it up simultaneously. And there's some giant clock that they're keeping track of the time between all these different signals. It's a computer clock. In fact, you can increase, if you had a quantum network, you can increase the accuracy of this clock. But right now we don't have a quantum network. So they just use the classical internet clocks. Now what they do is by picking up the signals from many different locations with known delay times, because they know what the geometry is. It's a very subtle thing, but it turns out that any one of these radio telescopes by itself cannot produce an image. It's just a point detector. It can't make any image. But since all these telescopes are distributed over a very large location space, namely the entire Earth, they can then put all those signals together and create an image actually of what the black hole looks like. So quantum technology can improve this imaging of astronomical distances in two ways. One, it can improve the clock by having quantum signals sent to a central atomic clock. And secondly, if you can now combine, if you can combine the electronic signals from the telescopes, instead of combining them through a classical internet, if you can combine them all, here's a quantum computer over here. If you can combine the signals from all these different radio telescopes into one quantum computer, then you can process the image much more precisely and get a much better image. So these are very futuristic applications. Maybe these are 20 years out into the future, but I think in 20 years we'll be seeing science that's being driven by all this quantum technology. Okay, how do I get out of this here? I have to stop. How do I stop that? When will I have it? Yeah, 10 years, 20 years, the end. Okay. If anybody's interested in a little more detail about some of these topics, there's actually a book that I wrote 5 years ago, which is called Quantum Physics, What Everyone Needs to Know. And it's available in paperback for about $10. And it goes through all the quantum key distribution business and a whole lot of other topics, some of which are not in this short course. Okay, so are there any questions that people would like to ask here?
There are a couple of questions about heralding and post-selections of with quantum memories. Do we need post-selection? Do we need heralding? When do we need heralding?
Do you want to address those questions? How do I?
So I believe, well, we do need heralding, at least with the protocol that you've shown here. I do not think we need post-selection for at least for this protocol. I mean, as long as
where should we go? Maybe to this protocol here.
I think the other slide of the memories.
The
Raman, yeah.
memories. Yeah.
So, and again, it depends on your experiment. It depends on your case. I would say that as if you have a case, for example, where you use spontaneous parametric down conversion, you don't have deterministic generation of entangled pairs. You do need some form of heralding to know if you have correctly generated and charged a photon in the memory.
Mm-hmm. Yeah, you could herald right here.
Yeah.
Yeah, then you know you have the photon here.
Yeah.
That's right. Yeah, so it depends on the details.
Yeah.
That's right. Any other questions here?
No. There are two questions that they ask if we can suggest a comprehensive textbook on quantum communication.
Oh, yes, I can. It's by Peter Rodi. And it's written at an intermediate level. So it doesn't go through all the mathematical proofs, but it discusses at a level much higher than the one we've just done today. And it's a very well-written book. Peter Rodi is a professor in Australia, I believe. It's a good one. Anything else?
They ask if there are... Oh, well, yeah. So they ask if I herald one of the two entangled photons, don't I lose it?
Yes.
Yes, of course.
Yes, you do. But the other thing you could do is you could use both photons like this. You use them both for something. But of course, now that doesn't work because you don't herald. The fact that you get no click here and no click here doesn't tell you that a pair of photons was generated back here. So that doesn't work in this particular case. You really want to have a herald here in this particular case. Yeah, you do want to have a herald. And it does destroy that photon. That's gone now. But that's okay. You still have the one photon. Anything else? If not, maybe we'll move on to the end again. The end. Okay. Uh, the book, which is also translated into these several different languages. Okay. So finally, we'll bring Belicia on here if she wants to say a few words about the course evaluation survey, or would you like me to say that, Belicia?
I'm good with either. I just talked to Brianna, and Brianna stated that the evaluation survey will be going out sometime this week. So it won't necessarily be immediately after this, but please keep a lookout in your emails. We would greatly appreciate it. Thank you, guys.
Okay. Okay. So the link will be provided in an email later. Right. Okay. Any further questions? We still have more time if anybody wants to hang out anymore. I can stop sharing though. Okay. People are slowly leaving. That's great. Hey, everybody, we really enjoyed having all your questions. They were really good. In fact, I noted down some of your great questions, which we'll be able to use in future courses that we're presenting here. And remember that the rest of the week is filled with more advanced courses. So if this course was very challenging for you, you might not want to try the other courses. They're pretty mathematical. But if this course fit what you're interested in, and you know more math and quantum physics, you could sit in on more or all of the rest of the courses this week. If that is all, then we'll say goodbye and happy quantum communicating. Bye.
Goodbye.